Those are the 2-6 notes for calculus 1. Let's start with the definition here. So a function is considered continuous at some point A if the graph of the function does not contain a hole or break at A. Okay, so that is an important definition that we're going to be utilizing. Just note that another way to write that, or another way to say that to sort of help you understand it a little better, is if you are drawing a function, if you have to pick up your pen for any reason, whether there's a hole or whether you have to continue it someplace else, then you automatically know that it is not continuous. Okay, that's sort of a key. So think of it as if you have to pick up your pen, pencil, whatever it is, to write it, it's not continuous. Small footnote, if the point of a function is indeed not continuous at A, then consider A to be a point of discontinuity. It's just a technical term that you have to know. So let's look at the example. It says graph to the right represents the cost in dollars, which is over here, of parking over a certain amount of time in minutes. Okay, so this is parking cost over time. So if you recall, this looks a little bit like our step function that we have seen before. It says, is this graph considered a function? Okay, so this graph is definitely a function, but students will often get confused a little bit by it. Just remember, we're dealing with the vertical line test. Okay, the vertical line test here. So if you draw a vertical line anywhere on this graph, is it going to intersect in more than one point? It is not. So empty circle, full circle, and so forth, all the way through. So that makes this definitely a function. Next, if so, is it continuous? Okay, so you should, just by the little graphic that I put up here a second ago, in order to draw this step graph, don't I have to lift my stylus to do that, my little pen that I have? Absolutely. Like I start here, have to lift my pen, go here. I have to lift it again, go here. Therefore, this is definitely not continuous in any way. So if we were to identify our points of discontinuity, then we have to identify any point where we actually have to lift the pen. Well, this point is part of our function, so we have to lift it at 0 to go up. So one of our points is 0. Where do we have to lift it again? We have to lift it again at 15, and then again at 30, and then again at 45, and we don't know anything over here, so we wouldn't call 60 a point of discontinuity. It could be just the end of the graph. So these would be our points of discontinuity for our problem. Okay, so just reading on here. It says, while it is relatively easy to determine continuity in the graph above, that's not always the case. It says the oscillating graph to the left shows very little about the behavior around the origin, so there needs to be a more formal definition of continuity. So what does that mean? Well, if you kept zooming in on this area right here, we could guess that it's continuous at 0, but do we really know for sure? We could keep on zooming in on this over and over and over again, and we might never get to the point where we can actually see what's going on at 0 to know that it's continuous. So that's why we need a formal definition. So in this scenario, we have this definition, what's called a function f is continuous at a if the limit as x approaches a of f of x equals f of a. If it's not continuous at a, it's called a point of discontinuity. Sorry about the dog barking. My pup was doing the zoomies downstairs, flying around the house and barking. Anyway, so this continuity equation right here. So we're going to break that down more when we're actually doing a problem, I think is the best way to do it. I mean, I think hopefully you can see that if you plug a in here, then you should get f of a over here, but you don't really get the understanding of what it's about until you actually, do the problems itself, right? So I think that's the best way to accomplish this, but I want to mention something here. It says, While this is the formal definition for continuity at a point, it is worth adding that in order for us to utilize the definition, we must know the limit of x goes to a of f of x and f of a exist before concluding that they are indeed equal. So what does that mean? Well, that's the two sides of this equation. So we have to show that this exists first. We have to show that this is not undefined. And then we have to show that they're equal to each other. And we do that using what's called the continuity checklist. So the continuity checklist, if you look at it, step 1, prove that f of a is defined. Step 2, prove that the limit on the left side here exists. And finally, step 3, prove that 1 and 2 are equal to one another. Okay, that is the key in the scenario of what we're doing. So it says, let's take a look at the first function comparing cost to time. We know that the function is not continuous, and we showed the points of discontinuity where t is equal to 0, 15, 30, and 45. So this should be t here, okay, because the axis is t. So it says, note, let's use our new continuity checklist to prove it. If you look closely at every point of discontinuity, they all fail one item on the checklist. Okay, let's do it. So let's sort of hone in on 15 because it's a little hard to see over here. So let's just look at the number 15. So that would be in this scenario, we're looking for f of a. So we're looking at a is 15. So is there an f of a for 15? So if you look up here, is there a value up here that 15 actually takes? And it turns out it does. It's actually equal to 0.25 right here. Not here because there's an empty circle above it, but right there. So the function value, there is a function value at a equals 15. But if you go to 2, does the limit exist at a equals 15? So as we approach 15 from both sides, does the limit exist? No, it does not. It is approaching a different value. So isn't that what's going to fail in each one of these? Isn't the limit going to approach a different piece from each side? So the answer to this is basically number 2 of continuity checklist. Fails every time. Okay, so what does that mean? Basically, the limits do not exist. Okay, that's just sort of like a summary, which is number 2. So in this scenario, that broke the continuity checklist. So you don't have to go on to this one. Once something breaks the checklist, that means we can automatically conclude that there is no continuity occurring. So think of it this way. I gave you a fancy method, not fancy, quite the opposite, of picking up the pen. Very informal, right? So I gave you that as a way to determine continuity. So this is the calculus formal way to prove that something's not continuous, which we could use in a scenario like this if we needed to. Okay, so let's do a formal example of this. It says you should realize from our first example that the graph to the right cannot be considered continuous. So yeah, duh. So you're going to have to pick up your pen a lot to draw this sucker, obviously, right? So this is definitely, not continuous. It says determine all points of continuity to start, and then use the continuity checklist to determine why the function is not considered continuous at all of these points. Okay, so that's a typo there. S is out. Okay, so basically, this is a multiple step problem. So by the way, on an exam, I would have you pick one of these. Like I would give you a problem that has one point of discontinuity and have you do it. But this is just great practice to do it for all of them. So I'm just going to write points of discontinuity. Okay, so let's start with the first one, which hopefully everybody sees. We start here. Where's the first time we pick up our pencil? At x equals 1. Okay, so at x equals 1, we have to determine where this might fail, essentially. So we have to go through the continuity checklist. So let's do it. So first things first, our first step, we go back to here. We have to determine if f of a is defined. So is there an f of 1 on our graph? Okay, if you look up from 1, there is no value of f of 1 on our graph. There's just a hole, and there's nothing above or below it there to fill in the blank. Therefore, f of 1 is undefined. So we already know that step number 1 has broken the checklist, and we would determine that by the way, we already know what's the point of discontinuity. We know it's not continuous, but what I'm saying is what step blows it up? That's what we're doing right here. So in this case, the first one, x equals 1, step 1 blows it up. And as I said, you don't have to go to the next steps. What's the next step of continuity? Well, the next, if you keep on going, we have to pick up our pencil at x equals 2. All right, so let's go through the checklist for that. So first thing we have to do is we have to determine, is there an f of 2? Okay, in this scenario, a little bit different. If we go up, there's again a hole, but if you look up a little bit further, there's actually a value of the function at 2, and it's equal to 3. So the first part of our checklist is checked off, and we move on to our second one. What's the second one? The second one wants to know if the limit of x goes to that value of a exists. So we have to figure out, does the limit as x goes to 2, our a, of the function, does that actually exist? So let's look, does it? So if we approach from the right side and the left side, approach 2, does it approach the same value? It turns out that it surely does. It approaches a height of 1. So therefore, so far so good. We have made our way through 2 parts of the checklist. What about 3? Well, number 3 asks, is the limit as x approaches 2 of the function equal to f of 2? So note, what is that? That's this and this. So don't we have those numbers? So basically, I don't know why I wrote if. It should say is. Is this the same? So the left side is 1. And is that equal to the right side, which is 3? So 3 and 1. Is it? No. So this breaks the checklist, which means we know that this is not going to be continuous at this point. And by the way, we knew that already because we have to pick up the pencil to make the point over here before moving on to the rest of the graph. All right, let's try another one. So let's do the next point of discontinuity appears to be at x equals 3. Right, first part of the checklist, we want to know if f of 3 exists. It clearly does. If we go up to this point right here, it exists at 1. What about the limit? We want to know if the limit of x approaches that same number 3. Does that exist? Okay, so if we go in there and go, well, let's look at the left and the right side as it approaches, clearly it does not exist. They approach a different value, so this blows up the checklist. So far we have every scenario of every step blowing it up. So you kind of understand why I showed this to you, to make sure that you know each step. So when's our next point? So if we keep on going here, all the way through the graph, the next point where I have to lift my pen is actually at 5. It appears that there's actually a vertical asymptote at 5, so that's a good point, definitely a point of discontinuity. So let's take a peek at what that's about. So I don't even know what's in there. Okay, this is number 1. So we have to find if f of 5 is defined. Well, clearly, if it's a vertical asymptote, it is undefined, because there is no value of y above the 5 on this line. So therefore, we have undefined, and this already blows up. So basically, this is a great example of having to see some of the scenarios this happens. But what I want to point out very specifically is that the two major areas where we have discontinuity when it comes to the graphs we make normally are at holes and asymptotes. And that's where it happens on this graph. We do have scenarios where it breaks into pieces, of course. So like this breaks into pieces, but it started with a hole when we had to move the pen. So just note that that is a common thread when it comes to functions that we deal with. Okay, and that's basically going to come up more with what we're going to deal with now. So let's talk about polynomials and rational functions when it comes to continuity. So it says a polynomial function is continuous for all x. Okay, well that's easy. So anytime we get a polynomial, we automatically know it's continuous. Why do we know it's continuous? Because there's no holes in a polynomial and there's no asymptotes in a polynomial. So how is it going to stop? What's going to make it stop? There's nothing. So we know polynomials are always continuous. But rational functions, there's an issue. With rational functions, because it's a fraction, we have to worry about q, and specifically when q is equal to 0, so we have to make sure it's not. So this is part of seeing that it's not continuous wherever it's not in that problem. So what I did was I brought a function with us. I believe it's a function that we have seen before, but no matter. Basically, what do we need to do? It says, for example, suppose we are asked to find all points of discontinuity for the following rational function, determine them analytically, and then verify with the graph. Okay, so again, we have to determine when q is not equal to 0. What's the best way to do that? It's to factor and simplify. If we factor this, we're going to get x minus 2, x plus 1, and this, we're going to get x minus 2, x plus 2. Okay, if we simplify, some very important things basically happen. So what's left? Actually, let's do this. So this is going to be equal to x plus 1 over x plus 2, but we know that x cannot be equal to what number? So in class, I would be eyeballing all of you trying to get this result, obviously. And hopefully most students are going to remember that this is an issue still. So even though it canceled out, it's still there in our original function, which means that x cannot be equal to 2 in this problem. So what do we get from this? Well, the denominator of our fraction is what creates our vertical asymptote. But then this is the what in the function. Hopefully everybody's screaming in their head, hole. Okay, look at the graph over here. Look at our vertical asymptote at x equals negative 2. So it's right here. See it? X equals negative 2 right here. So we got that. And then look at the hole at x equals 2, which is located right here. Okay, so if you look at our graph, if we started here and started graphing, we have to pick up our pen, start again here, keep on going. We have to pick it up because there's a hole and start again. So where are the points of discontinuity? They're at anywhere there's an asymptote and asymptote? Okay, how about an asymptote and a hole? So we would say the points of discontinuity are at x equals negative 2 and 2. So by the way, what do students muff up on exam situations? Or even on the lab? When I ask for the points of continuity, once they eliminate this, they pretend it doesn't exist. So they tell me that there's only one point of discontinuity at x equals negative 2, because that's where the asymptote is. So you need to update your knowledge of this to what we're doing in calculus, in the fact that this is still in the original function, and that is definitely a point of discontinuity. Alright, so let's return to piecewise functions. So remember, piecewise functions look like this right here. These are often popular for continuity problems, and it makes sense because you usually start one function, end it, and then start another one. Sometimes you don't. Sometimes they're connected together. They're just a different function. So it's an excellent spot for doing this. So what we're going to do is, it's going to be pretty crazy, it says determine the values of x, if any, for which the following piecewise function is discontinuous, then utilize the continuity checklist in order to verify. Okay, so this should be interesting. So first things first, if you look at the two pieces of the function, both of them are polynomials. What do we know about polynomials and continuity? They are always what? Continuous for all x. So we don't have to worry about any points of continuity on either of those polynomials themselves. So the only point of discontinuity must exist where the function is broken up. And at what number is it broken up? At x equals 2. So the only point of discontinuity that we have to check is x equals 2. Okay, that's our point of discontinuity. Okay, so here's the thing, though, which is not always, students don't always understand. So if you're looking at a graph, let's say, I don't know what this graph actually looks like. I guess we could graph it on Desmos, but just generally, like if you have a graph that's like a parabolic in nature, let's say the first one, and then it ends somewhere, and then the other one is a cubic in nature and it begins someplace else, let's say there, we don't necessarily know if this and this are connected. I don't know if that's hard to understand or not. So just by looking at our piecewise function, we don't know whether we had to lift our pencil to get to here, or it just leaves where it left off and goes from there. So in reality, this point of discontinuity that we're testing might not actually be a point of discontinuity. Right now, it's only a possible point of discontinuity, if that makes any sense. So this could start and begin in the same place. Like if it was a line and a parabola, who says it couldn't do that? But then again, who says it couldn't do this instead? We don't know. And I just want to point that out because not all students understand that. So we need to test this. So let's go through the process, which will be a little bit different. So first thing we want to do is f of 2, our point of discontinuity. So is there an f of 2? Well, forget the graph. Let's talk about this analytically. Let's talk about this algebraically. Where does this function exist? At which function does this exist at the value of x equals 2? Well, the equal to here tells us it's there. So f of 2 is 2 squared plus 3 times 2 minus 5, which gives us the value 5. So that means right now the first part of our checklist checks out. We actually have an f of 2. Let's go to the next one. Does the limit of x approaches 2 of our function, does it exist? Okay, is it actually a thing? So this is where things get a little bit more complicated because we have normally what would happen is we would go to the graph and we would draw arrows on both sides, but we don't have the graph. So we actually physically must look at this and go, all right, we have to find the one-sided limits or this is actually not going to work. So what do? We actually find the limit as x approaches 2 from the left of our function and the limit as x approaches 2 from the right of our function. Okay, so what I'm going to do though is I'm going to quickly replace this to save some space. So if we're looking at the limit of x approaches 2 from the left, which one of these does that actually happen in? It has to happen where it is less than, so that's this function. So what I'm going to do real quick is I'm going to replace that with this. Okay, and we're going to find that. Now, what about this one? So clearly, if we look at this function, x cubed minus 4 exists to the right of 2. So this has got to be x cubed minus 4. Okay, so how do we accomplish that? We basically just sub in 2 into the function. So here's the problem. A lot of students will look at the plus and minus and they'll start going, wait, isn't this one where we have to go to 1.9 and 2.1 and we have to find whether it approaches blah, blah, blah? No. Why? Because this is an irrational function. This is a polynomial. With a polynomial, we just plug in the number. When we plug it in, we get 2 squared plus 3 times 2 minus 5, which we've already calculated to be 5. Over here, we get 2 cubed minus 4, which is going to be equal to 4. Okay, so we have our limits. So the question is, does the two-sided limit exist? So the limit as x approaches 2 of f of x does not exist. Why? Because these two numbers are not the same, which means the checklist item number 2 blows up, and we can conclude that this is a point of discontinuity right here, and basically the whole entire function is not continuous. Okay, that was our verification for that. Okay, so this problem is effectively done, but I need to talk about something else in terms of this process. So let's just, for argument's sake, say that this ended up being 5. What does that mean exactly? That means that this graph would be one of those where it actually connects. So even though the graph changes direction, you would actually not have to pick up your pen, and it would be a continuous graph. Another important part of that, so if this was 5 right here, that means that the two-sided limit also would have been 5. But when we move to, let's say, step 3, which we're not going to, what's that step? It's to determine if this and this are the same. And they would have been both 5, and we would have determined that this was continuous. So if you look at this entire process, as long as this is defined, which it almost always is in these scenarios, how do we actually prove that this actually becomes a continuous function? Believe it or not, we just have to show that these two are the same value. So in other words, we have to prove that the limit of x approaches a from the left and a from the right are the same value. Okay, this comes into usefulness in the next problem. It says we can also reverse the process and determine a value that ensures continuity. That's the type of problem it is, ensuring continuity in a piecewise function. For example, determine the value of a for which the function below is continuous at x equals -2. Okay, so here's a. So that's why what I was explaining in the last problem. So in order for a function to be continuous, this limit must exist, and it must be the same as the function value that we have up here. Okay, it must be in order to make this work. So what does this do for us? Well, if we can somehow prove that this is equal to this at 2, then we automatically know that this is continuous. So we must ensure continuity by setting our two equations equal to each other at 2 and finding the value that makes that happen. So how do we do that? We set a to the x minus 2 equal to x squared plus 2x minus 6, but we need to do it when x is equal to our value -2, which is right here. That is the process in doing an ensuring continuity problem, because we need to find what value of a ensures that these two are going to be the same value, because that forces a situation where you would have, let's say, a line and then another function taking over but not lifting the pen in our problem. So let's do that. It's going to be weird, but let's do it. So we get, this is going to be a times -2, which is -2a minus 2 equals -2 squared, which is, I'll just write it out, -2 squared plus 2 times -2 minus 6. I'm actually, just for argument's sake, I'm going to write this the other way. So this is a times -2. Okay? So now let's rewrite it. So it's going to be -2a minus 2 is equal to 4 minus 4 minus 6. Okay, 4 minus 4 minus 6. So we're going to get -2a minus 2. This is going to be 4 minus 4 is 0, minus 6 is -6. If we add 2 over, we're going to get -4, which means a is equal to +2. So what does that mean? Excuse me, for the part of the problem. That means that if this a right here is 2, then that means that if we would not need to lift our pencil to draw the function 2x minus 2 and the function x squared plus 2x minus 6 at negative 2. We would literally be drawing a line and then starting again to draw the parabola. That's what that means for the scope of this problem. And yes, it is a line and a parabolic shape in this problem. So, for example, if I change this number right here, this a, to let's say 3, then what would happen? This would happen. You would get something that looks like the line starts not equal to, and then this would be an open circle and it would continue again. So in order to ensure continuity, this is the process that we must take in our problems. Okay, sorry for the delay there. My recording software kind of self-destructed. So let me try to wrap up this lesson real quick. So at the bottom here, it says another method for expressing continuity is with intervals. Just as we identify a point of discontinuity, we can also state the interval at which the function is continuous. Okay. So essentially, for number 5 here, it says find the interval of continuity for all of these problems, or these functions. So what are you doing? You're trying, in interval notation, I need you to just express wherever this function is continuous. So what are you basically leaving out? You're leaving out all points of discontinuity in the interval. So if, for example, if you had a polynomial, just for argument's sake, so if you had like 2x squared minus 3x plus 1, right? So the interval of continuity would be negative infinity to infinity. Why? Because polynomials are continuous on their entire domain. So we would say negative infinity to infinity. But I'm more interested in writing the ones that aren't continuous on their all domain, because those are the ones that students struggle with. So what do? So for g of x, which is for letter A here, if you look in the denominator, we've already seen this before. I need to change that at some point. But we've already learned basically that we're dealing with points of discontinuity at 2 and negative 2. Okay, so we can, if you want, we can do the factoring. So we're basically going to have, so this guy and this guy, x plus 2, x minus 2 in the denominator. So this is going to be x plus 3, x minus 2 in the numerator. So if you're looking at this scenario, clearly these cancel out, but that doesn't matter when it comes to continuity. We know the denominator, 2 and negative 2 are points of discontinuity. So once we know that, points of discontinuity at x equals positive negative 2, then we can write our interval notation for our continuity interval. So where do we start? Continuous starting at negative infinity, but then where do we reach our first point where we have to pick up pencil? Negative 2. We always put a union symbol to connect it back together to negative 2, because then we put it back down and start writing again. Note the parenthesis tells us that it doesn't include that value. So essentially there's a hole right there, or an asymptote. For us, we know that it's an asymptote, by the way. So then where's the next spot? We go to 2, where the actual hole is. We start again and we go all the way to infinity. So this would be the interval of continuity for this problem. And by the way, what also is it? It's the domain in scope of what we're doing. So we need to do the same thing for all our other problems. This is usually a pretty easy one. Just remember not to remove the 2, the hole, from the problem when you're determining it. Okay, so what else? So the radical 2x minus 1. So for radical 2x minus 1, you're basically looking at a scenario where we have to come up with an interval of continuity. But when it comes to just general root x, what do we know always has to be true under the radical? We know that x must absolutely be greater than or equal to 0. Okay? How do we know that? Because if it's negative, we have the square root of a negative, which means we're in imaginary world, imaginary units, and that's not what we want. So how do we determine in any old problem what the continuity interval is when there's a radical? We have to make sure what's under the radical is positive, essentially. Now, note, it can be equal to 0 because we can have something equal to 0. That's a number. So what do we need to do? So over on the side, we need to do that 2x minus 1 has to be greater than or equal to 0. We solve this inequality, add 1, and then divide by 2. We're going to get x has to be greater than or equal to 1/2, which means any value that we plug into this equation that's greater than or equal to 1/2 creates a number result, a real number result. So for example, look at 1, the number 1. If we plug 1 in there, 2 times 1 is 2, minus 1, square root of 1, good. That's a good number. That works. And it's also a place where this function is continuous. But if we put 0 in there, we get 2 times 0 is 0, minus 1 is the square root of negative 1. So this is an imaginary result, and therefore it's not continuous in the real number system. So it wouldn't be continuous there. So what's our continuity interval? We have to start at 1/2, including it, and then go to infinity on the right side. So that is going to be our interval. Okay, so beginning again at C. Now note, all I did was I took root 2x minus 1 and I put it in the denominator. So what does that affect? What does that change for the purposes of our problem? What does it alter? Well, again, we need what's under the radical to be positive. But what can't the denominator as a whole be in any fraction? It can't be 0, which means we don't want 2x minus 1 to be greater than or equal to 0. We want it to be strictly greater than 0. Okay, so what does that mean? If we solve it, it's going to solve the same way, except we're going to get x is strictly greater than 1/2, which means any value strictly greater than 1/2 that we plug into this function, we will get a real number answer, and it will be continuous. So what does that mean? We're going to get the similar result to here, but we have to make sure that we don't put it in the square bracket on the right. We get 1/2 to infinity as a result. Anywhere else is not continuous. So let's just do one more scenario of importance here, just to make sure that all is good with understanding. So this is the ultimate problem right here in terms of understanding. Why? Because we have a radical in the numerator, but we also have in the denominator an x minus 10, which rules out another number that this can't be. So we have a bunch of things going on. So let's start here. So the root 2x minus 1 is in the numerator, right? So this is going to be a greater than or equal to issue. So again, what do we have? We know that we're going to need to be on this interval again, right? So we know we're back to this. 1/2 to infinity with the bracket on the left. But what does this bring up in the problem? This brings up that x cannot be equal to 10. Here's the problem. Isn't 10 located in here? It is, which means that what we need to do is we need to eliminate it. So 1/2 to 10, union 10 again to infinity. And this is our interval of continuity for our problem. I do think that some students struggle with B, C, and D. Why? Because they have trouble under the domain in general, and domain and range were just like nutso-butso for students. But in general, you just have to be very careful with where it's continuous. So you're looking for where it works, or in other words, what's the domain of the function in the majority of cases.